Alright, hello everyone. Today, the problem we're looking at is the USACO 2020 December contest gold problem 1 of replications. So this is a gold problem, and I would say even for gold in February, it's kind of hard. So do you want to pause the video first and look through this problem yourself? Here's the samples. Alright, so I assume you already read through the problem. So basically what this problem is asking for is you're given a grid of size at most 1000 by 1000, and now there's as starting spots of those self-replicating robots, kind of like the von Braun robot. I'm pretty sure it doesn't matter. There's like this one term in physics in which a robot replicates itself. Anyways, so these robots, every second, a robot replicates itself onto every grid on the 4 directions next to it. And then now you're trying to, and there's also rocks, all right? So you can't replicate a robot onto a rock, and when that does happen, all robots stop moving and stop replicating. So now you're trying to determine how many grids, including the starting grid, how many grids are there possible that might be reached by a robot? Like whether it's the replicant or the original robot itself. And the robot can move in any of the 4 directions also. So every second, it moves and it replicates. All right, that's the 2 things it does. And now you can start from any of the 3 points, any of the several starting points given the input, and now you're trying to determine how many spots could be occupied by a robot. So here's a diagram, the sample analysis. So basically, look, you have a robot, you move, right, replicate, and then you move, and then you can't replicate again, because if you replicate again, you touch a rock. Okay, so you can pause the video once again and think about this. Okay, I assume you give this problem a try already. I say this is really difficult, so I'd be impressed if you can actually figure out this problem on your own, because I was able to do most of it, but on the last step, I got stuck. So yeah, I mean, it's a gold problem. It's reasonable. So basically, what's the first of all, when we see this problem, there's actually 2 parts to it, right? Because we need to know which spots can be reached by the original robot and which spot can be reached by the replicants of the robot. So basically, what my idea was is to run 2 BFS. Basically, the first BFS to determine where the original robot can be, and then the second BFS to find where the replicants of every single spot that an original robot can occupy will also occupy. I know that's kind of hard to understand. So basically, what I'm saying is, let me pull out a drawing here. All right. So this is a grid, right? Basically, what I'm trying to do is to find all the spot where an original robot can reach, and then for every single spot, you push it into a BFS queue, right? Basically, and then you find where its replicants can also occupy, right? Say it's that area, for this one, it's that big area, for this one, it's only this little bit, right? So basically, that's my idea. However, this problem is actually not that simple. First of all, we need to know how many times a robot can replicate itself on a certain spot, right? So we need a DFS pre-processing that. So for any certain, let's say this cell, we need to know how many times max it can replicate itself on that spot. And that's actually just going to be the shortest distance of this block from any rock, right? Say the green ones are the rock. So how many times can it replicate itself? Well, obviously, it's going to be the distance from this robot and its closest rock, right? In this case, it's going to be that one. So this is all the space that can be occupied by the replicants of this robot at this cell. And so now we can pre-process that. So then for each spot, we know how many times it can replicate itself. And now we can run another BFS, starting with every single starting point, pushing them into the queue first, and then finding out the spot where every single original copy can reach, right? But now here comes the second hard part about this problem. After you found out where each original copy can reach, say let's use red to denote that, right? All these spots are original robots. Sorry for my bad drawing. But all these spots are spots that can be reached by an original robot. Well, now we need to find where the replicants can reach. But if we just simply BFS, if we just use the value that we got from the first pre-processing, the maximum number that it can replicate, and then just do that for every robot and add that to the answer, we're gonna have some grids to be counted multiple times, right? Like that one. That's counted 2 times by both this and this. And also it's gonna be inefficient because then maybe a grid is BFS multiple times, which would cost a time complexity of n cubed, which is actually n to the 4th, right? Because you have n squared nodes, you have n squared cells, and if you iterate through each cell with every other starting point, it's going to be n to the 4th, which is definitely unacceptable for n equals 1000 for this problem, right? So we need some smarter way. So the solution, my original way was just to keep track of how many replications, like for each grid, instead of marking whether it's visited or not, we mark how many replications like can be made at this grid the last time it's visited. So say at for this original copy, right, it visits this grid, right, and when it reaches this grid, we can still make, say, for example, 2 more replications, right? So you can do this and then this, and you reach that 2 more replications. And now, if we're BFSing for this one now, sorry, that's not a good circle, but say this is the center of that circle, right? And when you reach this grid, actually you can still replicate for 5 more times, right? You can replicate 1, 2, 3, 4, 5 until you reach the edge of how many times this robot can replicate. So if that's the case, well then we iterate through this point again. That was my original idea, just to keep track of how many times we can replicate on this cell after the last time reaching it. However, that's still going to be n4th time complexity. So it's actually a smarter way that a solution offered. So for each grid, actually we don't keep track. We still just use one array of v. We still only keep track of 0 or 1, denoting if it's visited or not. However, this time we push it into not just regular queue like regular BFS, but push it into a priority queue. So basically, we use a priority queue storing the t, meaning how many more times it can be replicated, the x, the x value, and the y value. We store a triplet like this into a priority queue. I'm just to say PQ here, right? And then since priority queue is descending, so we're gonna always pop out the maximum t first, right? And then every time we pop the top of the queue out, which is going to be a max t, we just mark that grid as visited and never visit again. And how do we know it's right? Well, obviously because we already know that this t is the maximum out of everything else in the queue. And since every time we iterate through another point in the queue, all the sum of this, well, it's not really the sum, but all the 4 directions next to it, it's all going to have a t of t minus 1, right? The new t is going to be the t of this center grid minus 1, right? Because you can make 1 less replication now. So basically now, since we already pushed out the biggest t out of this entire queue, there's never going to be another cow that can possibly reach this grid with a higher t, because the t is going to be subtracted by 1 every time. So with this smart method of using a priority queue instead of regular queue, this is a very clever way to resolve the problem of having it into the 4th complexity. And that's how I implemented with this program. So here it's a really massive code. I think it's like 300 lines or something like that. But here's the input, right? 2 for starting point, 0 for regular point, and 1 for rock. The first BFS, we pre-process the array of, what is it called again? M, yeah. M equals the shortest distance from every point to a rock. So that's how many times you can replicate on this spot. We pre-process it with a BFS and store it in M. Now the second BFS is where the original copy can reach, which is going to be stored in R, I'm pretty sure. Yeah, array R, which is stand for where the original copy can reach. And now, for every single point that original can reach, we push it into the priority queue Q1, with the third term being how many times you can replicate on this spot. Right now, we have this priority queue, and then we iterate once again through all these queue, but this time with T in descending order, unlike just regular BFS. So this is actually really smart, because now the time complexity is only n squared, which with n being 1000 is acceptable. So now this is how you pass this USACO 2020 December contest gold problem 1 of replication. I would say this is kind of hard actually, even though there's not much actual complicated algorithm involved. You have BFS, right? Obviously priority queue, that's just like standard silver level data structure. So this actually can be a silver problem, and I say it's problems of this level is going to start appearing in silver or silver US Open now that it's 2024. But I hope this video helped. Thank you. Okay, so the problem review part of this video ended. So from now on, it's just going to be a report on the grinding progress of the USACO. All right, so today's the first day that I'm actually able to commit to the plan of making a video every single day on problem review. But, today's also the first day of winter break. And I didn't actually do as much work as I thought I would. I only mocked 1 USACO, which is going to be like 4 hours. And I thought I really could have done a lot more, but, good enough. First day of winter break, still getting into grinding mode. And I did manage to solve one problem today during the mock contest, which is quite disappointing, but it's also a really hard one. So yeah, good enough. And this problem I solved, I'm pretty sure like 2 months ago or something. I think I solved it in October, so it's been a while, and it took me a little bit to like actually recall what I did for this problem and come up with this editorial problem. Which is why that I'm choosing to do videos on old problems like this, so that I can, so like every problem is gonna be a week after I solve it that I actually do a video review over it. So I'm actually reviewing this problem myself when I'm making this video. So yeah, I feel pretty good for the first day of actually committing to the plan, and I hope I can follow this for the next what month? Yeah, until January 24th. Yeah. All right. Hope this video helped. Thank you so much for watching.